Today, we are diving headfirst into a global race. And the stakes? Well, they're so high they could redefine pretty much everything we know about computing. No, this isn't just about making our gadgets a little faster. This is about building a completely new kind of machine that could solve some of humanity's biggest, most impossible challenges. Welcome to the quantum computing race.
And that quote right there, it just nails it. We are not talking about an incremental upgrade, like the next iPhone. We are talking about a fundamental leap into a whole new reality of what's possible, tackling problems that our best supercomputers today would take millions of years to solve. This is exactly why governments, tech giants, and scrappy startups are all pouring billions and billions of dollars into this field. The payoff could be, literally, world-changing.
So what is it that makes these machines so revolutionary? I mean, what's the big secret? To really understand the race, we've got to pop the hood and take a look at the engine that's driving it all, the bizarre yet incredibly powerful rules of quantum physics.
Okay, so here's the first mind-bending idea. A regular computer bit, the kind in your laptop, is like a simple light switch. It's either on or it's off, a 0 or a 1, simple. But a quantum bit, or a qubit, is more like a dimmer switch. Thanks to a wild principle called superposition, it can be on, off, and kind of everything in between, all at the exact same time. It's this ability to explore countless possibilities at once that gives quantum computers their horsepower.
And if that wasn't strange enough, then you've got entanglement. This is what Einstein famously called spooky action at a distance. Imagine you have two coins that are magically linked together. If you flip one and it lands on heads, you instantly know the other one is tails, right? Even if that other coin is on the other side of the galaxy. Entangled qubits work just like that, creating this incredibly powerful, interconnected web that lets them perform calculations that are just impossible for normal computers.
So with all these qubits and all these states, how in the world does a quantum computer actually find the one correct answer? Well, it uses something called interference. The best analogy is noise-canceling headphones. A quantum algorithm is cleverly designed so that the waves of all the wrong answers crash into each other and cancel out, while the waves for the right answer build each other up, making the solution stand out loud and clear.
All right, so now that we've got a handle on the quantum engine, let's take a look at the different cars on the racetrack. Because it turns out there isn't just one way to build a quantum computer. Nope, we've got several competing designs, and each one has its own unique set of strengths and weaknesses.
As you can see, it's a pretty crowded field. There are a whole bunch of competing technologies out there. You've got superconducting circuits, which are kind of the frontrunners right now, but you also have trapped ions, photonics, and a few others. Each of these is like a different bet on how to build the most stable, scalable quantum machine. And honestly, it's not at all clear yet which design is going to win this race.
And this whole race, it's really all about trade-offs. Take superconducting systems, the kind that giants like IBM and Google use. They have the fastest processing speeds, which is great, but they're also really prone to errors. On the other hand, you've got trapped ion systems. Their claim to fame is super high fidelity, meaning they're incredibly accurate, but they're a lot slower. Then you have these newer kids on the block, like neutral atoms, which might just be the key to scaling up to millions of qubits. But that tech is still pretty new.
So, now, let's head over to the paddock and meet the actual teams. Because this race isn't just about the technology, right? It's about the companies and the brilliant people behind it all, from these massive tech corporations to these really focused and agile startups.
The playing field pretty much breaks down into four main groups. First, you've got your heavyweights, the tech giants like Google and IBM, who are trying to build the whole shebang, from the hardware to the software. Then you have the pure-play leaders, companies that live and breathe quantum and nothing else. And right alongside them are specialized innovators and a whole wave of new startups. You see, the real battle isn't just to build the best chip, it's to control the entire quantum stack, the hardware, the software, the cloud services, all of it.
And just look at the different strategies between two of the titans. IBM is all about scale and access. Their game is to get their quantum systems into the hands of as many developers as possible through the cloud. Google, on the other hand, is taking a more focused, high-risk, high-reward bet. They're trying to build one near-perfect, error-corrected quantum computer. It's a way harder problem, but if they pull it off, it could be a complete game-changer. It's that classic battle of breadth versus depth.
And you see a really similar dynamic among the specialists, the pure-play companies. You've got IonQ, who's chasing that dream of a universal high-fidelity quantum computer using their trapped ion tech. They want to solve any problem you can throw at it. But then you have D-Wave, a real pioneer in the space.
They took a totally different path with something called quantum annealers. These machines don't solve every problem, but they are commercially proven today at solving really complex optimization problems for big businesses.
So why? Why are all these brilliant people and these incredibly powerful companies pouring so much money and effort into this race? Well, it's because the stakes, both the potential rewards, the prize, and the critical dangers, the peril, are just astronomically high. Just let that number sink in for a second. Over $700 billion. And that's not a one-time prize. That's a conservative estimate of the annual economic value that quantum computing could unlock. We're talking about an economic disruption on the same scale as the internet or artificial intelligence. That is the prize that has everyone racing for the finish line. And where's all that money going to come from? Well, it's about completely revolutionizing research and development. I mean, imagine designing new life-saving drugs molecule by molecule, or creating brand new materials for ultra-efficient batteries, or optimizing global financial markets to perfection. These are the kinds of huge, intractable problems that quantum computers are being built to solve.
But here's the peril. The dark side. The same incredible power that can create new medicines can also be used to destroy. A powerful quantum computer could, theoretically, break the encryption that protects everything from your bank account and your private messages to top-level national security secrets. And the immediate threat is something called harvest now, decrypt later. It means that right now, adversaries are hoovering up our encrypted data and just storing it, waiting for the day they have a quantum key to unlock everything.
Okay, so what's the solution? We need to start future-proofing our data, and the answer is something called post-quantum cryptography, or PQC. These are basically new encryption standards that are designed to be tough enough to resist attacks from both classical and quantum computers. And the really key message here is you have to act now. This isn't a quick fix. It's a multi-year transition that companies and governments need to start, well, yesterday.
So with this incredible prize on one hand and this really urgent peril on the other, let's look at the road ahead. What does the timeline actually look like? And what major obstacles are still standing in the way of somebody crossing that quantum finish line?
First thing to know, this is a marathon, not a sprint. Right now, we are in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, our systems are pretty powerful, but they're also error-prone. The next big phase, which should start around 2027, is all about achieving quantum advantage, which is when these machines finally start solving real-world problems better than our best supercomputers. But the true disruption? That's coming in the 2030s, with the arrival of large-scale, fault-tolerant machines.
But look, the road to that quantum future is absolutely full of major hurdles. For one, qubits are incredibly fragile. A tiny vibration or a change in temperature can mess up a whole calculation. That leads to high error rates, which we're still trying to fix. And scaling up from a few hundred qubits to the millions we'll need for those big breakthroughs, that is one of the biggest engineering challenges of our time. And on top of all that, we need a whole new generation of scientists and programmers who actually know how to write software for these revolutionary machines. This strategic map really shows us exactly where the race stands today. It's all a trade-off between how mature the technology is right now versus its potential for the future. And the biggest takeaway here? Nobody, not a single player, is in that ideal top right corner yet. Every single team has huge challenges they still need to overcome. The leader of this race could change tomorrow. It is still anybody's game. So that leaves us with the big question. In a race defined by such immense complexity and absolutely unprecedented stakes, who will be the first to claim the quantum future? With all these competing technologies, clashing strategies, and massive challenges still ahead, the answer is far from certain. The only thing we know for sure is that the stakes couldn't be higher. A complete redefinition of what's possible on one side and a threat to our entire digital world on the other. The race is on, and the world as we know it is waiting at the finish line.